Alright, we're back with part 2 of section 3.4. I did leave this last question, part C, for you to try on your own, and I do hope that you actually did this one. Once again, we're asked to take this equation and make a sketch of what the curve looks like. And to do this one, I'd like you to follow the same steps as the one before. So the first thing I'm going to ask you to do is tell me the degree. And if you said 3, you are correct. Notice what the leading coefficient is. The number is 2, so it's positive. Okay, the key part is positive. So from this, you know that the end behavior should be as follows. If you remember correctly from section 3.1, what quadrant does it start in if it's an odd degree polynomial with a positive leading coefficient? If you said 3, you are correct. And where do you end then in this case? You start down low and it's odd, so you always end opposite. You end high, so you end in quadrant 1. Okay? So even with all this information, you can do a quick sketch. Okay? I'm going to do a really small sketch over here right now. Okay? With this information, I know that we have something that starts in quadrant 3, ends in quadrant 1. It's degree 3, so you would expect that there would be at most how many x-intercepts? Right, 3 of them. 1, 2, 3. Okay, so you would expect, okay, 3. I should say not 3. I'll say at most 3. Okay, at most 3 x-intercepts. Okay. Now, to figure out the x-intercepts is the hard part for this one. Because unfortunately this is not in factored form, we need to rewrite into factored form before we can identify the x-intercepts. And how can we rewrite this in factored form? I gave you a hint last time. Yes, welcome back to section 3.3. Use the factors theorem to help you out. So I'm going to take this equation here, and I already noticed one thing to make life a lot easier. You see how there's a 2 in front? Now we're supposed to use that rational root theorem, but look, every single term seems to be, or every single coefficient seems to be an even number. So what I'm going to do is ask you to factor out the 2. And that makes life a little bit easier, and I hope you can see why. Because by factoring out the 2, now I have just x cubed. And now I can use the integral zero theorem to help me find one of the possible zeros. So looking at here now, using the integral zero theorem, now you don't need to write this in your notes, but I'm just showing you right now. The possible roots are, I hope you remember, I guess you look here, right? You look at the constants. So plus minus 1, oops, plus minus 1 or plus minus 2. Okay? Now, remember how we're supposed to test out numbers now? So that's a little bit difficult sometimes, or tedious. I'm going to show you a little quick and easy way to do this as well. Okay? So what I'm going to ask you to do, if you have a graphing calculator, is to pull it out, please. And I'll pull mine out right now too. And with your graphing calculator, I'm going to show you how you can evaluate numbers in an expression and do this quite easily when you have to repeat the same expression over and over again. Okay? So, we're going to test out numbers now, right? We're going to test. So let's just test out, let's say x equal to negative 1. So what you would actually do is you plug in negative 1 to the expression, right? And so you would actually type this all out into your calculator, and the goal here is to find something that equals to, if you said 0, you're correct. Okay. So this is what you would do. Negative 1 cubed minus 4 times negative 1 squared plus 5 times negative 1 minus 2. Negative 12. Oh, painful. And then now the question is, I gotta do this again for other ones, so you gotta change it. Oh, that's so nasty. Well, here's what you can do. Your calculator actually stores values for x. So what you can do is type in -1, and you see this store key that's just above the on sign? Press that store key, it gives you an arrow, and then press X. So what that does is it tells the calculator that X now has the value -1. So if I now did X plus 5, it will evaluate this expression with X being -1. So -1 plus 5 is 4. Okay, let's say I did 100 times X. Well, that would be then -100. There you go. So if I want to evaluate this now, I'm going to type in X cubed minus 4x squared plus 5x minus 2, and voila, it evaluates. I get -12. Okay, now here's the exciting part. -12 didn't work for me, so let's choose another one. Let's choose something like x equals to 1. Well, instead of typing it out again, this is what you can do. Back to the calculator now. I'd like you to store the value of 1 as x. So press 1, then that store key again, and then press X. Once again, the store key is just above the on key. Press Enter. So now the calculator knows that x always is the value of 1. And now, if you want to evaluate this into that polynomial again, the one up here, x cubed minus 4x squared plus 5x minus 2, hey, you don't have to actually type this in again. Watch. You see this button, the Enter button? On top there's this thing called Entry that's in yellow. If you press second Enter, it brings back the previous entry. So I don't want to bring back that previous entry. I want to bring back the other one before that. So do it again. So repeat this second entry feature. Second entry. See how I get that back? Now if I press enter, it's going to evaluate this expression using the number 1. Boom. Perfect. 0. And therefore I found a factor. Woo! So x minus 1 is a factor. And this is great because now I can use it to try to factor this cubic. And so now to factor, I'm going to either use long division or synthetic division. I'm going to use synthetic division just because I'm a little bit lazy and I don't want to write out all those things. So -1 from the x minus 1 factor. And by the way, if you don't know this stuff well, you obviously haven't done enough homework for this section from before. Go back and try some of these questions. Okay? Everything in math builds on each other, and if you don't have the good foundations, you're not going to do well in this course. Okay. So once again, we're going to bring down the 1. We go 1 times -1, which is -1. We then subtract the terms. -4, take away -1 is -3. -1 times -3 is 3. 5 minus 3 is 2. -1 times 2 is -2. And this works because -2 take away -2 is 0. That last term here is the remainder. These terms are the coefficients of your answer, and it's always going to be 1 degree less, so it becomes 1x squared minus 3x plus 2. So now I'm going to take all these pieces of information, this one and the factor, and that's equal to that. So let me rewrite this now. So therefore, I'm going to say y is equal to 2, and instead of having that cubic, I now have x minus 1 times x squared minus 3x plus 2. And if you think you're done, think again, because I can factor this trinomial, figure out two numbers that multiply to 2 and add to -3. Remember this stuff from grade 10. And if you need practice on this, let me know too. Factoring is important in grade 12. How about -2 and -1? That would be great. And there you have it. You've now factored this. And by the way, what was the point of factoring all this again? Just to give you some more work and a headache? For you to find out the actual zeros. So the zeros here is x equal to 1, x equal to 2, well, x equals to 1. So this seems to be a double root. Okay? So you think about it then, your graph or your equation should look something like this. I've got 1, I've got 2, it starts down low, it goes up to 1, it comes back to 2, and it goes up like this. Okay. One last thing you could do is just find the y-intercept. That's when you let x equal to 0, so y equals to 2 times 0 cubed plus, minus 8 times 0 squared plus 10 times 0. Well, anyways, it's -4. So here is -4. Okay? So I hope you can check your answer with mine, and if you got it right, bravo to you. And if you got it wrong, well, figure out what you did wrong, make the changes, learn from this, please. Okay, new stuff today. Page 4, example number 3. So we're going to continue on this journey in equations and graphs of polynomial functions. Here I'm going to ask you to actually find equations given information. So I'm not giving you graphs, I'm just giving you information, and you have to find the equation that matches the information. So for example, in part A, I'm asking you to find the equation with a cubic function that has zeros at -1, and notice that means multiplicity of 2, that means there's 2 of the zeros at -1, and 3 and a y-intercept of -6. Well, a cubic function. Okay, cubic means cube, right? Now, when I say zeros at -1, what factor creates a 0 at -1? Yes, the factor is x plus 1. And because I say it's the multiplicity of 2, what do you think I need to put on top of this x plus 1? Yes, I need to square it, because there's actually 2 of the same zeros. And there's one more over here, 3, so of course that'd just be x minus 3. Okay? Now, you see how this is cubic? So you have x and a square and an x, so x times x times x gives you x cubed. That's good. This is an equation, so I need a y equals to. And because this is just a general one, I want a specific equation with this information. We're going to put a constant in front, the value of a. And we did this last year with the parabolas as well. So same idea here. How do you solve for a? Well, that's where that last piece of information comes into play. A y-intercept of 6 is the same thing as the coordinates of the point. Yes, 0, -6. Remember, y-intercepts when x equals to 0. So to solve for a, I'm going to suggest to you plug in the point. So -6 becomes y, x is 0, and let's see if you can now solve for a. And -6, that's just 1, -3, -3, a equals -6. I think from there a equals to 2. So therefore, now the equation is, by the way, those 3 dots are therefore, a, which is 2, x plus 1 all squared, x minus 3. Done. Okay? I'm going to ask you to try B on your own now, please. It's very similar, so go ahead and try. I will keep quiet. You try it, come back after, and double check your answer. Go. Okay, here's the answer. -112, x plus 1 cubed. And you could write x minus 0, but it's just easier to write down x squared, I think. X minus 1. Bravo, if you got that. All right. We're going to do 2 more examples here, and that'll be it for chapter 3. So I hope you are getting on track. You will have a celebration of learning coming up very shortly. make sure you get all your homework done or you can't get this celebration of learning in your hands. Okay, here's an example here where I'm asking you to find 3 consecutive integers that have a product of negative 60. So you're going to have to use some algebra here to see if we can come up with an equation that represents this statement. And we're going to try to solve the equation to find the solution. Okay? Anyone know what consecutive means? Yeah, one after the other. So 1, 2, 3, 10, 11, 12, negative 4, negative 3, negative 2, they're all consecutive numbers. So how can we represent consecutive numbers algebraically? Okay? Well, if I let the first number be x, what would the second number be if they're supposed to be consecutive? It's one more here, right? So x plus 1. Well, what would the third one be then? Right, x plus 2. So then, using this setup, find 3 consecutive integers that have a product of negative 60, you do something like this. X times x plus 1 times x plus 2, and that should equal to negative 60. Okay? And then we can expand this out. So I'm going to take these two here first and try to expand this. So we have x squared plus, and then I'm going to do things together. 2x plus 1x is 3x. 1 times 2 is 2. We'll now distribute the x from the outside of the bracket. And then I'm going to move everything to one side. And now you have to solve for x. How can you solve for x? Well, you'll have to do the factoring and all that kind of stuff. Okay? Now, this is okay, but you know what? It's getting kind of messy. So, some people think, there's too many terms there, it's not so fun. I'm not going to try that. And that's fine, okay? If you like it this way, go ahead now and do the long division or synthetic division, find the answer. I'm going to show you another way to kind of set up this idea of 3 consecutive integers. That maybe makes the algebra a little bit easier, okay? Or, the goal here is to try to make your algebra easier. And I'm thinking if you strategically chose what x would be, life might be just a little bit easier. Let me call the middle number here x. And so if the middle number is x, what's the third number going to be? The one that's a little bit more. Well, yeah, that's x plus 1. Well, what would you write as an expression for the first number? And if you said x minus 1, I like it. So now when you multiply things together, it becomes x minus 1 times x plus 1 equals to negative 60. Now, I'm going to multiply these two together first because I see that x minus 1 times x plus 1 becomes just a difference of squares. It just becomes x squared minus 1 times x equals negative 60. Well, this looks a little bit nicer for me because now I have x cubed minus x. I'm going to move the 60 over to the other side, and hey, this is a little bit nicer. I'm still going to have to do that factoring and whatnot, but you know what? Smaller, less terms, it's a little bit better. So now I'm going to try values. So once again, we're looking for 60, so you can go plus minus 1, plus minus 60. Oh, there's a lot for this one. Plus minus 3. I might be out of space. Oh no! Lots of stuff here. But once again, I like to try the numbers that are very small first. Oh, there's a lot. I'm not going to forget it. You figure it out. Okay. I'm thinking one of these has the correct answer, and this is where I think having the graphing calculator is great. And so if I asked you now to store 1 as x, and let's try this out, x cubed hold on. Got a phone call. Oh, somebody took it. X cubed minus x plus 60. And we enter. Oh, that's 60. Obviously, 1 doesn't work. So let's write this down. Tried x equal to 1. Not good. How about x equals to 2, right? You can keep trying things, and so much easier to try now. 2 stores x, recall, so second enter, do it twice. Oh, that doesn't work either. Okay, try 3. Enter, enter. Oh, now notice the number's getting bigger. So I'm thinking, maybe not the right way of doing it. Let's try some negatives. So maybe I'll try negative 3. Maybe I'll just randomly try that. Negative 3 store x. Yeah, enter, enter. Oh yeah, well, 36, it's okay. Let's try negative 4. Right? So I'm going to try all these things. Second enter, second enter. Oh yeah, so ultimately x equals to negative 4 works. Therefore, x plus 4 is a factor. Then you can do the long division. Okay, 4. And then now I'm using this equation here. So 1, negative 1, 60. Is there a problem with what I just did there, everybody? Please say yes, because I forgot to add in the 0 terms. Can you see that I do not have an x squared term? So therefore I need to put a place value holder, the 0. Okay, don't make that mistake. Okay, we're going to do the synthetic division now. 4, I'm going to subtract negative 4. That would be negative 16. We'll subtract, that gives me 15. This is good. So this just becomes x squared minus 4x plus 15. So therefore this actually becomes x plus 4, x squared minus 4x plus 15 equals to 0. You can try to solve this by factoring or using the quadratic formula. I'm going to tell you that you actually can't solve for this. There's no solution, so therefore x equals to negative 4 is the only solution. So therefore, if x equals to negative 4, what are my 3 consecutive integers? Remember, I'm asking you to find 3 consecutive integers. Well, since x equals negative 4 is the second number, the first number must have been 1 less, which would be negative 5. And the third number is 1 more, which is negative 3. Negative 5 times negative 4 times negative 3. Yes, that gives me negative 60. Bravo. Okay. So here's a quick standard example. But before I move on to the last thing for today, I do want to kind of point out to you, well, how would the polynomial equations have changed if instead of me saying 3 consecutive integers, I've now changed it to 3 consecutive even integers? How do I ensure something is even? Well, if I were to take x as any random number, in order to make it even, I can always multiply it by 2. So therefore, you could take the first number being 2x, right? First. Well, what would be the next even number? Is it 2x plus 1? Well, remember, 2x is an even number. If I add 1 to an even number, it always becomes odd, so I don't want that. I want the next even number. I should add 2. Very good. The third, that'd be 2x plus 4. Perfect. Now, how would the equation have changed if I said, hey, give me consecutive odd integers? How do I guarantee that something becomes odd? Well, I can guarantee something becomes even by adding or multiplying it by 2. How can I make it odd? Yeah, you can either add or subtract 1. So perhaps I'll do 2x minus 1. The second then would be 2x plus 1. The third could be 2x plus 3. Now, by the way, some of you may say, well, why did you subtract one? Why not add one? Okay, I'll add. Doesn't matter. Still the same idea. Oh no. Don't tell me I lost this stuff. Alright. Hold on. Alright, I'm back. Sorry about that. Computer froze. Probably doing too much work tonight. Well, let's take a break, just like you, I'm sure. So anyways, here, 2x plus 1, 2x plus 3, 2x plus 5, that works as well. Okay? Alright, one last question. Okay, so here's another example of how we can use polynomial equations. Alright? So this one says, the diagram shows how a piece of cardboard can be used to construct a box with a top. So you think about it, I'm going to take this big piece of cardboard and I'm going to cut off some parts. So the shaded parts are cut out and aren't used. So hopefully you can see this. This would be like the bottom. And the matching top would be here. And these are the four sides of the box, right? We take off those shaded pieces and we fold them up. We make a box. So the question here says, write a cubic function which gives the volume V of the box as a function of x. Now, x seems to be the little, I guess, the measurement of how much you're going to cut off this corner here. So let me call x, let x be the amount cut off on the small square. Okay. So, how do we find volume again? Length times width times height. Good. So on this diagram, you're going to have to tell me which segment here represents the length, which represents the width, and which represents the height. So hopefully you can imagine the bottom. So I'm thinking, well, the bottom, this must be the length, and I'm highlighting yellow. That's length. And then when I'm highlighting blue here, that must be the width. The question I have is, what's the height? And if you said this part here, yes, that's the height. Very good. That's the height. So let's see if we can find expressions for each of these pieces. Okay, let's look at the length first, the yellow piece. Well, we know the entire vertical piece of this cardboard is 28 centimeters, but the length is only that yellow piece there, so I'm actually taking away from it these two pieces here, and they're both length of x. So therefore, L is not 28, but it's 28, what? Yeah, minus 2x. There's your length. Well, how about your width then? The width is just that blue part. And we know the entire distance from here to there is 32. Well, since they're the same, these two parts are the same, we can chop it in half. And note that this distance here is only 16. But that's still not the blue piece that represents my width. That's still too much. So what do I have to do there? Yeah, take away this purple piece, which is x. So my width is actually 16 take away x. The height is that purple piece. Well, what's the expression to represent that purple piece there? Yeah, that's just x. So here we go. Here's my volume. And to make it look a little bit nicer, I'm going to ask you to expand this out. 28 times 16. What's that? 28 times 16. Even I don't remember right now. 28 times 16. 448. Okay, 448 minus 28x. I'm just doing this part first, by the way, right now. Expanding it out. Minus 32x plus 2x squared. Still an x there. Well, 448. 28 and 32, I think that's 60. Gonna multiply this by x as well. 2x cubed minus 60x squared plus 448x, and there's my equation for volume. Okay. I also said include the domain. So what are my possible values for x? x represents that height. So what's the smallest the height could be of a box? Yeah, 0. So you know that x has to be bigger than 0. Now the question is, how big can x actually go? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look at the diagram. So imagine this x here growing bigger and bigger and bigger. How far or how big can it grow? If you said 28, I'd say not so fast. Because don't forget, you also have an x on this side. So this grows as that one grows. So therefore, if you're going to share the growth here, it's not 28, but 14, right? Half grows from the bottom x, the other half grows from the top x. So your domain is actually x can't be bigger than 14. If it's bigger than 14, guess what? You don't get a box. All right, so the next part here says how many centimeters should be removed from each dimension in order to create a box with volume of at least 960 centimeters cubed. So now I'm saying to you, what is x really? Because that's the how many centimeters should be removed. So what is x so that the volume of this box is at least 960 centimeters cubed? Now, I'm just going to make a quick table of values to illustrate how the volume changes as we change x. So x, once again, is the number of centimeters that we changed, and then v is volume. Alright, so let's take a look. If I were to choose x being equal to 1, so I'm only going to cut off 1 centimeter off the edge of that piece of cardboard, what would the volume be? Well, because you have the equation for volume from part A, just all you need to do is plug in 1. I'll use my calculator, and once again, be smart. 1 storing as x, then go 2x cubed minus 60x squared plus 448x, and you have a volume of 390. So that's way too small. I want at least 960. Well, what happens if it's 2? Okay. We can then store 2. Okay, and then we recall. Man, this is getting kind of tedious. Oh, 672, not bad. Okay, let's try 3. 3 store x. Now, you could keep doing this, but, you know, this takes a little while. 8 getting close. So what's another way we can figure this out? Now, I'm going to use our graphing calculator to do this, because ultimately, before I use the graphing calculator, let me show you how you can do this by algebra. Because I said at least 960 centimeters, that means your volume equation, 2x cubed minus 60x squared plus 448x, must be at least, meaning greater or equal to, 960. Okay, and if you wanted to do this, you can solve this cubic inequality. Now, I know I haven't shown you this yet. I don't know if I actually will right now, but for those of you who want to, you can. Combine what you learned with inequalities last year in Math 11 with the idea of finding the zeros, which you learned last section, that you can do this. But instead of doing that, I'm going to propose that we actually use the graphing calculator to actually help us out. Okay? Because I want you to once again see the visual connection of this equation. So what I'd like us to do is in y1 type in the equation for volume. Okay. So I'll do this with you right now too. So y equals 2 now. Remember how I did that entry feature? Well, it works here too. Second enter, boom, it's right there. Great. Okay, if you graph it out by not changing the window, you're going to get something weird. So let's see if we can change the windows. Remember the x values? Well, we told you earlier or above, remember up here in part A, the domain has to be x is between 0 and 14. So why don't I just make x min 0 and x max 14? Y stands for the volume. The smallest volume you have is 0. And notice I want the volume to be at least 960 centimeter cubed. So use a number that's bigger than 960. I'm going to try maybe 1250 just so that I have enough room. And let's see what happens when we graph. Well, here is part of this cubic function. If you think about it, the cubic function goes down like this and then comes back up and down and up. And of course, the other parts don't matter to us. It only matters here. I guess I'm thinking, where is it at least 960? So to show the 960 part, I'm going to ask you to go back and in Y2 type in 960 because that's the volume. So over here, if I type in 960, we'll get this nice horizontal line. And I'm asking you for where is it at least 960. That means the graph is above this horizontal line. And to figure out where it intersects, we're going to use the intersect feature. That's number 5. Let me move my cursor to the first intersection point on the left. Okay. Just get it close by, press enter. It'll default to the second curve, press enter, and then it'll give me the actual intersection point. So x equals to 4, so when x equals to 4, you get y equals 960. So I'll give you a little hint here, find the intersection points. Okay, that's one of them. There's another one, so let's go back and find that. Second calc, press 5. Scroll to the right. Press enter, press enter, press enter, and there's x equal to 6. So if I wanted to figure out where it is at least 960, well, the solution here must be x is bigger than 4 and less than 6 for the volume to be at least 960. And we can just do a quick sketch too. Here's 0, here's 14. Here's my y1 equation. Whee! Here's my y2 equation. Whee! And then here's my intersection points. 4, 6, 960. There you go. Now we've done chapter 3.